everybody, welcome back to Measure Theoretic Probability. We have been talking about almost sure convergence for a sequence of random variables, and we're going to do some more examples today. And the rest of the time, we are going to verify some things that most people probably wouldn't bother verifying, but I just want to do it one time, and then in the future, I will gloss over these things like everyone does. And what I mean by that is in the last video, we looked at maybe the limit as n goes to infinity of xn and computed some things, and I used the fact that that limit was in fact a random variable. And we haven't proven that if you take a sequence of random variables and define a limit, that that is in fact a random variable, which is essentially another measurable function. So again, people probably don't worry about these things, but I just wanted to do one video on this sort of thing. So let's start off with another example of almost sure convergence. Suppose my space consists of a non-empty set omega, which is the reals between 0 and 1 inclusive, and my sigma field is the Borel sets on 0, 1, and my probability measure is the Lebesgue measure, which is length, and because the total length of this interval is 1, it is in fact a probability measure in this case. I'm going to take any little omega between 0 and 1 inclusive and define xn of omega to be omega to the n. So I'm defining a sequence of random variables, or am I? Is this in fact a random variable? Bear with me on that for a moment. Let's just talk about convergence right now and then worry about that detail. Note that if omega is greater than or equal to 0 or strictly less than 1, then omega to the n, as n goes to infinity, is going to 0. On the other hand, when little omega is actually equal to 1, then xn of 1 is 1, no matter what n is. So we have a sequence of 1s, and the limit as n goes to infinity of that sequence of 1s is just 1. I'm going to define a limiting random variable, just an x of omega without a sub n. I'm going to define it to be 0 if omega is greater than or equal to 0 or less than 1. And I'm going to define it to be negative 13 if omega is equal to 1. After all, this point where omega is equal to 1 is a set of probability measure 0. It's a set, the singleton point with length 0. So I could define x this way, and we do in fact have that xn converges almost surely to x. So that's the end of this problem. If it was to show almost sure convergence of something, yes, I could have replaced this negative 13 with a 1 or really any other number, but it's just an example. So the detail that I want to go into today is stuff like this. Is this, in fact, defining a sequence of random variables? Let's take a look at this a little more closely. So one way we can verify that xn is, in fact, a random variable is to take any real number, little x, and consider the set of omegas for which xn of omega is less than or equal to little x. I'm going to plug in what xn of omega is, and then I'm going to solve for the omega. So we have the set of omegas for which omega is less than or equal to x to the 1 over n. Now, what I wrote over here assumes that omega is in capital Omega. And a lot of books, and rightly so, will put that in here in place of my omega. They'll start by saying little omega in omega such that. I should be doing it too, but I just wanted to stress for you that that should be your assumption every time I write down a set like this, that we are talking about omegas from the set omega. So rather than write that in here a little better, I'm writing it the same way I always write it, but making sure you know what I mean. We have some cases to consider here. X is any real number, and if x is negative, then this omega less than or equal to a negative, actually, let's go back to this set. The set of omegas for which omega to the n is less than or equal to a negative number. None of them, because the omegas here are coming out of the interval from 0 to 1 inclusive. So this is going to be the empty set. Whereas if x to the 1 over n is positive or non-negative but less than 1, that's the same thing as saying that x is non-negative but less than 1. And in this case, the set of omegas for which omega is less than or equal to this number that's non-negative and less than 1 is just all the omegas from 0 included up to x to the 1 over n included. And so this is what we get for the set of omegas whenever x is greater than or equal to 0 or strictly less than 1. And finally, if the real number x is greater than 1 or even greater than or equal to 1, then the set of omegas for which omega is less than or equal to this number So remember, these omegas are coming from the interval 0 to 1 inclusive. And so what omegas in there are maybe less than or equal to 3.8? That's going to be all the omegas from 0 to 1 inclusive. In all three cases here, what we end up with is, in fact, a Borel set on the interval from 0 to 1. Therefore, our function is measurable and is a valid random variable. Let's do another one with the same setup. So omega is going to be the interval from 0 to 1 inclusive, and curly f, the sigma field, is going to be the Borel sets on 0, 1, and p is going to be Lebesgue measure. Consider now for any omega in 0, 1 inclusive, the sequence of random variables defined like this. Xn of omega is omega to the n plus omega. Now, I'm not going to verify that this is in fact a random variable for each value of n, but now you know how to do that. So if I take any omega between 0 and 1 inclusive, I am going to define an x of omega to be omega. I have a little aside for you here right now. If you take real numbers a and b, a less than b, and in the interval 0 to 1, and look at the probability measure of the set of omegas for which x of omega is between a and b, because x of omega is just omega, this is the set of omegas for which omega is between a and b, and this is just the probability measure of the interval from a to b, which is the Lebesgue measure b minus a. Does this look familiar to you? We haven't talked about distributions in this course yet, but if you're here, I assume you've had some probability or statistics, and if you were wondering, this is how, and on this set, how we define a uniform distribution or a random variable with a uniform distribution. Remember, there is a PDF or probability density function, which is a curve under which area represents probability, and the uniform distribution on any interval, in this case, the interval from 0 to 1, is a flat line distribution because you want the area to be constant no matter what subinterval you're looking at. And so if we're looking at a subinterval from A to B, the rectangle will have a little rectangle with base b minus a and height 1, which will have area 1. And so that's the uniform distribution, even though we still haven't talked about distributions in here yet, or PDFs or anything like that. But back to the convergence issue, let's look at the set of omegas for which the limit as n goes to infinity of xn omega is equal to this x of omega. It's going to hold whenever, so here is my x omega. So whenever this disappears, that's when the limit of these guys is going to coincide with this guy. And that happens for all omegas greater than or equal to 0 or strictly less than 1. In other words, that's the interval closed 0 to open 1. And this interval has probability measure or Lebesgue measure 1, the length of the interval. So regardless of what is going on when omega is equal to 1, that singleton point, which has measure 0, we can say that x and omega is converging almost surely to x. And in fact, we do not have convergence at that single point. But again, it doesn't matter because we have convergence everywhere except for a set with probability measure 0. Now I want to leave behind almost sure convergence for just a little bit and talk about making random variables from other random variables. Suppose I have a probability space consisting of a non-empty set omega, a sigma field curly f, and a probability measure p. I'm going to let capital X, capital Y, and then a whole sequence, capital X1, X2, etc., be valid random variables on this space. As mentioned, I want to talk about other random variables that can be formed by operations on these random variables, and also some sets that are described by behaviors of these random variables and show that those sets are in the sigma field curly f so that it makes sense to take the probability measure of them. Once again, this is kind of tedious, not in a negative way. I think this is going to be a fun day, but not stuff you're really going to be thinking about as you're solving problems. In the last video, I went through some proofs, and in each line of a proof, I would suddenly come up on a probability measure of some set, and then I'd have to say, hey, does that set even make sense to be in the probability measure? And I think most of the time, you're not maybe thinking about things like that so much, especially when you just have a rote convergence in almost sure convergence problem to show for a homework. But Yeah, I want to do tediousness in this video, and I love tediousness. The first thing I claim is that if you look at the supremum or infimum of the sequence of random variables, x1, x2, etc., that is in fact another random variable. Let's take a look at one realization of the sequence. The realization is after you've rolled the dice, you've flipped the coin, you've done whatever, and you have some fixed numbers. I'm going to plot them here. And the supremum is a least upper bound for these numbers. It is, quote unquote, essentially a maximum, but it is the maximum, even if the maximum doesn't quite fall into the set we're looking at. And you'll note that, well, if we want to show that the supremum of this sequence is a random variable, we want to look at the set of omegas for which the supremum over n of xn omega is less than or equal to x, where x is any real number. How do I get the maximum of all of these points plotted over here to be less than or equal to x? I need each and every one of them to be individually less than or equal to x. So that means that this set can be written as an intersection as n goes from 1 to infinity of the set of omegas for which xn of omega is less than or equal to x. Again, this is saying every one of them is less than or equal to x, and that's going to happen if and only if the supremum is less than or equal to x. Because my sequence x1, x2, etc. were given as valid random variables, this sort of set is a set in curly F, the underlying sigma field for our probability space. And so these are sets in F, and this is a countable intersection of sets in F, and this is indeed, again, in F. Therefore, this is in F, and we have shown that the supremum of a sequence of random variables is another random variable. Or if you need it, the maximum of a sequence of random variables, if it exists, is another random variable. For the infimum, the way to get the greatest lower bound, or essentially the minimum, to be less than or equal to x is to have at least one of these points less than or equal to x. At least one. That's a union. The union of the set of omegas for which xn of omega is less than or equal to x. If you have a point in here, you have a point in here. In other words, if the infimum is less than or equal to x, then at least one of these xn omegas has to be less than or equal to x. So this is an equivalent set. And again, this is a set in curly F because the xn's are random variables, and this is a countable union, which is again in F because sigma fields are closed under countable unions, and we're done. We have shown that the supremum and infimum of a sequence of random variables, those are again random variables. And one more time, if the max and or min of the sequences exist, those are also random variables. I also claim that the lim sup or limit supremum or lim inf or limit infimum of the sequence are random variables. You might have forgotten what these are, but we have definitions, simple to follow, straightforward. Let's look at the set of omegas for which the lim sup over n of xn omega is less than or equal to little x, where little x is any given real number. The definition of this lim sup, and these are real numbers. This is not like a lim sup of sets where you define it in terms of unions and intersections. This is a lim sup of a sequence of real numbers. And you may recall this was defined to be the infimum over all n greater than or equal to 1 of the supremum over all m greater than or equal to n of xm omega. So this is the definition of this. And we want to consider the omegas for which this is less than or equal to some real number, little x. Given what we just talked about, if you want the infimum of a bunch of numbers to be less than or equal to x, that means you want at least one of them to be less than or equal to x, and that corresponds to a union when you look at the x's individually, and the supremum corresponds to an intersection when you look at the x's individually. So I claim that this set is the union as n goes from 1 to infinity of the intersection as m goes from n to infinity of the set of omegas for which x m omega is less than or equal to x. Now, the xn's are valid random variables, so these sets are in F, and this is countable unions and countable intersections. So again, this whole thing is in F. And because this is in F, that's one way we can show that this is in fact a random variable. Of course, the lim inf is very similar. The lim inf for a sequence of numbers as opposed to a sequence of sets is defined to be a supremum of an infimum. And if this sort of thing is less than or equal to x, then that means we need um, every, well, our supremums correspond to intersections and our infimums correspond to unions when looking at sets of omegas. This is in fact the intersection as n goes from 1 to infinity of the union, as m goes from n to infinity of the omegas for which x and omega is less than or equal to x. Because we started with a valid sequence of random variables, these sets are in F. And again, we've got countable unions and intersections of F sets, and those are again in F. And so showing that this is an F is one way to show that this is a random variable. Let's look at some random variables made from limits. So if xn of omega as a sequence, so x1, little omega, x2, little omega, etc., that's a sequence of real numbers. And if that converges for every single little omega in the set omega, then I claim that the limit that you get out of this is in fact a random variable. I used this in something in the last video without proving it. That was one of the things that sort of motivated me to make this video. And let's see why. How do you define this limit? We're talking about real numbers here when you put the omegas in. And a limit is defined to be the common value, if it exists, of the lim sup and the lim inf. And we already know that the lim inf of random variables and the lim sup of random variables are each, again, random variables. So each one of these, the lim inf and the lim sup, are valid random variables. We just showed that on the previous slide. So if the limit exists, it's one of these, it's both of these, and is in fact a random variable. Number 4, consider the set of little omegas for which the random variable x is equal to the random variable y. I claim that this is in the sigma field curly f. And why do I claim this, or why am I showing this right now? Because at some point in the very near future, I'm going to need to take the probability measure of a set like this. So I want to make sure this is in fact a measurable set. Now, we already showed last time that the set of omegas for which x of omega is strictly greater than y of omega, we showed that that was in F. That was in the previous video. Similarly, the set of omegas for which x of omega is less than y of omega, this also has to be in F. Just rename the variables. There's really nothing different going on here. Now, to get at the set of omegas for which x of omega is equal to y of omega, and just for practice, I'm going to write that as the set where x equals y, but this is notation for the set of omegas for which x of omega is equal to y of omega. How does x equal y? We do not want x to be greater than y, and we do not want it to be less than y. So if you consider the set where x is greater than y, union together with the set of omegas where x of omega is less than y, those are all the places where we do not have equality. So take the complement of that set, and this is one way to represent this set over here. And because this is an F and this is an F and this is a union and a complement and sigma fields are closed under countable unions and complements, this is in fact in F. So we have seen or shown right now the claim that the omegas for which x of omega equals y of omega is in fact in F. But wait, there's more. We had not the last one we just showed, but the property of 4, that if you look at the limit as n goes to infinity of x and omega, if that limit exists for all omega, that we get a valid random variable. Right now, I would like to restrict our attention to the omegas for which a sequence converges. I claim if we started with a valid sequence of random variables that this is in F. Let's show it. This set over here, if xn converges, how do you know it converges? We need the lim inf to equal the lim sup. The set of omegas for which xn omega converges is the set of omegas for which the lim inf of xn omega is equal to the lim sup of xn omega. Now, these are each individually random variables. We saw that today. And by the previous property, given two random variables, the set of omega on which they're equal, that is a set in F. So this was property 4 just before this property. Therefore, we have that this set is in F. So anytime I take a probability measure of something like this, it makes sense. So here is another thing that has come up for us already in the previous video, I think. If not, then we're going to see it eventually. Suppose that xn omega converges not for every omega, but for almost all omega. That is, for omegas on a set of probability measure 1. So there may be places, some omegas that you can plug into the sequence where you do not get any convergence. but collecting all those omegas, that should make a set with probability measure 0. So I claim, well, before we had if it converges for all omega, then the limit is a random variable. But I claim if we define a random variable to be the limit wherever the limit exists and define it to be something else, and this is really not that important otherwise, that we have a new random variable. This is a particular expression that I'm going to need, or I used in the last video. I can't remember, but I know I need it around this point in this course. And I want to prove something a little more general than this. So let's look at something a little more general than this. Recall that this set in here, recall that this set over here is in F. We showed that today. So let's look at something just a little, again, more general. Suppose that X and Y are random variables and A is a set in curly F, the sigma field. I'm going to define a new random variable, Z of omega, to be X of omega whenever omega is in the set A, and Y of omega whenever omega is not in the set A. This is the general case of the limit that I had on the previous slide. I claim that this is a random variable. Let's show it. So as a reminder, here's how we define Z. And I'm going to take any real number. I usually call it little x. I'm going to call it little z so it matches here. I'm going to take any little z real number and look at all omegas in omega for which z of omega is less than or equal to z. And you'll notice that I did write in capital omega here, even though you're always supposed to assume that's the case. It's going to be kind of important for this particular computation to really see that. I can rewrite this set of omegas as the set of omegas for which z of omega is less than or equal to z intersected with A, and then union that with the set of omegas here intersected with A complement. So I've broken this up into a union of disjoint sets. Over here, I have the set of omegas from the full omega such that z of omega is less than or equal to little z, but this intersecting with A says we better make sure that those omegas are also in A. In other words, this intersection is just the set of omegas in A for which z of omega is less than or equal to z. Similarly, this set over here is the set of omegas in A complement for which z of omega is less than or equal to z. Now, if I know that omega is in A or A complement, then I know that z is either x or y, so I can fill in the x of omega or y of omega, depending on where the omegas are. And the assumption is that x and y are random variables. So sets like this should be an F, but this is not usually what we look at. We look at all, we want to look at all the omegas in capital Omega, not just omegas in some set A. So I want to unravel this trick here and write this as the set of all omegas in omega for which x of omega is less than or equal to z, intersect that with A. So that's the same as this set. And this set over here, I want to write as the set of all omegas in omega for which y of omega is less than or equal to z, and intersect that with A complement. Now I've got things that look like the sets that we use to show that things are random variables. I know for sure that this is an F because X is a valid random variable. I know that this is an F because that was my assumption in the setup here. I know that this is an F because Y is a valid random variable, and F, a sigma field, is closed under complement. So if A was an F, A complement was an F. So all of this, we've got just some finite unions and intersections of sets in F, which is again in F. So we're done. We have shown that this is in F, and therefore have shown that if you take a random variable X and a random variable Y and a set A in the sigma field and define a new random variable like this, it is in fact a random variable. So I think that's enough for the tedious stuff of showing things that appear in probability statements actually should be in there are measurable sets, or showing things are actually random variables. But I am going to gloss over that probably in future stuff we do, but you'll be able to do it. So if you ever pause when I'm taking the probability measure of something and ask yourself, is it valid? Is that a measurable set? You would show it probably like we just did in these examples. Let's go back to almost sure convergence. I have a criterion for almost sure convergence. It's actually not that big a deal. I'm not really saying anything different here, as you'll see. But I claim that xn converges almost surely to x if and only if the probability that the absolute value of xn minus x is greater than epsilon infinitely often This needs to be 0 for every epsilon greater than 0. This is, of course, the abbreviated notation. This is a set of omegas for which this happens. But yeah, let's show this, that this is equivalent to this. So we can use this for showing almost sure convergence in the future. Now, this is not something I tend to show almost sure convergence with. If I was doing an exercise, like does this converge almost surely to that? I find this claim a little more helpful for proving other theorems about almost sure convergence, as you'll see in here. So I just said that we're not really saying a whole lot here. Let's see. Let's see why these are equivalent. I am going to call the set of omegas for which the absolute value of xn omega minus x of omega is greater than epsilon. I'm going to call this an. So this is like writing ANIO, AN infinitely often. And AN is this set of omegas. And yes, I should probably call this A sub n comma epsilon, or something that shows that this set is also defined by epsilon. But in giving this set a name, I can rewrite my claim like this. I can say xn converges almost surely to x if and only if the probability of the lim sup of the ANs is 0 for every epsilon greater than 0. And now I'm really regretting not having that epsilon in there because this looks disconnected. Let's take care of that. What is that AN infinitely often, or AN lim sup? We know by definition, this is the intersection as n goes from 1 to infinity of the union as m goes from n to infinity of the AMs. And just filling in what AM is, we get something that looks like this. So if I take a little omega from this set over here or this set over here, that means given this intersection, it has to be in every one of these. And given that this is a union, it has to be in at least one of these as m goes from n to infinity, except it has to hold no matter what n is. So we're saying here that omega is in the set ANIO if and only if there exists arbitrarily large values of n such that the absolute value of xn minus x is greater than epsilon. There's no finite n where you can cut it off and say that you will never have this distance above epsilon again. Uh, if we have almost sure convergence, we want to make sure that we have convergence on a set of omegas that have probability measure 1, and we do not if we have this property holding. So this property can only hold on a set with probability measure 0, and that's the claim. Xn converges to x almost surely if and only if the probability that this event an happens infinitely often with probability 0. Because basically the ANIO is a set of omegas that represent the ones that went bad when taking the limit. Fortunately, they only constitute a set of measure 0. Next up, I have a sufficient condition for almost sure convergence. So the last one I wrote was a criterion. It wasn't if and only if, but here I have if you have this, then you have almost sure convergence, but not an if and only if. I claim that if for all epsilon greater than 0, if we have the sum as n goes from 1 to infinity of this probability finite, then we have almost sure convergence. I love using this to show almost sure convergence because once you've computed probability, you have numbers, and then we're talking about limits, or in this case, sums of numbers, and we're back to comfortable territory. Let's prove this claim, this sufficient condition. Let's prove that if any epsilon greater than 0 gives us that this sum is finite, that we then have almost sure convergence. Learning from my mistakes with the epsilon, I'm going to define a set A sub n comma epsilon to be the set of omegas for which xn of omega minus x of omega is greater than epsilon. I didn't write the omegas here, but hopefully you know what I mean. So the setup of this proof, what we're given is that the sum of probabilities of sets like these is finite. In other notation now, we've got that the sum as n goes from 1 to infinity of the probability measure of the a n comma epsilon is finite. This was given as the setup for this theorem or claim. Now we're going to have to reach way back to the Borel-Cantelli lemma. There were two of them, and I'm going to use Borel-Cantelli 1. And that said, if A1, A2, etc. are sets from the underlying sigma field, if the sum of the probability measures of the AN is finite, then the probability of the lim sup set is 0. The lim sup of the AN, of course, being the same thing as AN infinitely often. In other words, the probability that infinitely many of the events occur is 0. This is the Borel-Cantelli lemma 1. In fact, I took this slide from that video. So we saw this a while back. So let's go back to our proof. And you can see that this statement is really just Borel-Cantelli 1. I think this was in lesson 11 or video 11 if you want to go check that out. This, however, the probability that the lim sup or the an epsilon IO is 0 is what we had in the previous claim, or yeah, I called it a claim. I didn't call it a theorem that we did right before this claim, that xn converges to x almost surely if and only if the probability of an infinitely often is 0. So now we know that xn converges to x almost surely, again, by the previous claim. So we're done proving this. So here's the claim we just proved. And what I'd like to look at now is a slightly stronger version of this claim. I am going to replace this epsilon for all epsilon greater than 0 with for any positive integer n. And then I'm going to replace the epsilon over here with 1 over n. I claim with these changes that xn converges almost surely to x. So first, I'm just going to talk about this claim and then prove it. And then at the end, talk about why I'm calling it a stronger claim than the previous result with the more general epsilon. I'm going to take any epsilon greater than 0 and find a positive integer m such that 1 over m is less than epsilon. Once you have your epsilon fixed, you can go high enough in the integers so that this quantity is below epsilon. Now note that if for any integer n greater than or equal to m, 1 over n is going to be smaller than 1 over m, so 1 over n is going to be less than epsilon. And if we look at the omegas for which xn omega minus x omega in absolute value is greater than epsilon, this is going to be a subset of the set of omegas for which the absolute value of xn omega minus x of omega is greater than 1 over n. Because it is easier to be larger than a smaller number. If I were to take the probability measure of both of these sets, I could use the monotonicity of a measure, in particular a probability measure, to say that the probability measure of this set is less than or equal to the probability measure of this set. Now, we do already know that this claim holds if instead of 1 over n here, I have an epsilon for every epsilon greater than 0. So I kind of want to take probabilities on both sides and use our previous claim to show this one. The problem with that is that if I put a probability measure on each of these sets, then I do have the probability of this is less than or equal to the probability of this, but it only holds not for all n, but for n's such that 1 over n is less than epsilon. So to help fix this in what is ultimately going to be our final statement, I'm going to consider the sum as n goes from 1 to infinity of the probability that absolute xn minus x is greater than epsilon. And I'm going to rewrite this as a sum as n goes from 1 only up to this m minus 1 plus the rest of the sum. So I've done nothing here but cut this sum up into two sums. For the second sum, I'm considering only n's that are greater than m, which means 1 over n is less than 1 over m is less than epsilon. So that means that this probability is, or let me back up. That means that this set is contained in this set with epsilon replaced by 1 over n. And using monotonicity of the probability measure, if I take the probability measure over here, I will get a larger probability when I replace epsilon with 1 over n. So far I've taken this probability and I've bounded it above, and let me push that just a little bit further. For this first term here, the biggest these probabilities can be is 1. So imagine they're all 1. That's the largest this term can be. So this line is less than or equal to m minus 1 plus, and now I'm going to bound this term over here. This is a sum of probabilities, which are not negative. They could be 0, but they're numbers between 0 and 1 inclusive. And if I'm summing up over n, going from m to infinity, and throw in more terms, the original, as n goes from 1 to infinity, I will only get a larger number or maybe the same if all those probabilities are zero, but I'm not including anything negative, so it's not going to get smaller. So this is less than or equal to this when I look at the full sum from 1 to infinity. For any epsilon, we can choose a finite m so that this can happen. So this is finite. And in this claim, I'm assuming that this sum is finite. And both of these things being finite makes this finite. And if this is finite, from our previous claim, we have almost sure convergence of xn to x. And that's what we wanted to show. So let's sum up where we are at this point. If xn converges almost surely to x, the definition is that the probability of the limit of the xn equaling x is 1. That's just the definition of almost sure convergence. We had a criterion that we proved today, and that was that xn converged almost surely to x if and only if the probability measure of the set where xn and x are more than epsilon apart infinitely often is 0 for any epsilon greater than 0. So we proved this one today. We then proved the claim that we have a sufficient condition for almost sure convergence if, for any epsilon greater than 0, the sum of these probabilities is finite, then we have almost sure convergence. And we just proved that we have this as well for any positive integer n. In the next video, I want to talk about some statements that were not if and only if, and show you some counterexamples about why the other direction, or an example of the other direction not holding. And then we're going to move on to convergence in probability and its relationship to almost sure convergence. So I hope to see you in the next one.